In this vignette, we're going to talk about cheetahs. Among casual wildlife enthusiasts, the cheetah is a widely popular predator and an emblem of conservation. Among evolutionary biologists, however, they are notorious for having very low genetic diversity, which is alarming considering that only 7,000 wild individuals remain. Take a look at this. This is an outbred domestic cat genome. Notice the red regions, which represent heterozygosity across alleles, whereas green regions represent homozygosity. This is an inbred cat genome, significantly more green regions by comparison, which makes sense in the context of inbreeding as it indicates lower heterozygosity among alleles. Now this is the genome of an outbred cheetah cub. As you can see, it's almost completely green. But how exactly did their genetic variation become so infamously low? The short answer? Population bottlenecks, or periods of small population sizes. But let's examine this a little more thoroughly. For that, let's go back a few thousand years to understand such bottlenecks and their negative effects on modern populations. Not only are cheetahs a unique feline species from a morphological perspective, having adaptations specifically built for speed, but they are also unique from a phylogenetic perspective. Modern-day cheetahs are the only representative of the genus Acinonyx, but it wasn't always like this. In fact, cheetahs didn't always inhabit Africa and Asia like we know the species today. During the Pliocene and into the Pleistocene, there are at least 4 paleontological species and 4 subspecies of ancestral cheetahs that span Europe, North America, Asia, and Africa. However, it is hypothesized that towards the late Pleistocene, approximately 100,000 years ago, there was a migration of North American cheetahs across the Bering Land Bridge. This resulted in subsampling populations in both Eurasia and Africa, creating a founder effect, otherwise referred to as the species' first genetic bottleneck. Likely due to this reduction in population size, and by extension unique alleles across individuals, inbreeding among these populations likely increased, resulting in lower heterozygosity. This may sound bad enough, but with cheetahs populating multiple continents beyond Africa and Asia, how could this situation get any worse? Simple. Another bottleneck. Roughly 10 to 12,000 years ago, at the end of the Pleistocene epoch, approximately 75% of large mammals living in North America, Europe, and Australia went extinct. Many attribute such extinctions to changes in climate and human hunting pressure. At the same time, however, a monophyletic group of cheetahs was restricted to a range of Central, Eastern, and Southern Africa. This is considered the species' second bottleneck, as all extant populations of the species were now restricted to Africa, as well as a tiny subset in Outrun. Now, with all this information in mind, how exactly has such genetic variation been analyzed? How do we know genetic diversity in modern populations is so low? With advancements in genome sequencing and analysis, we can obtain insights into how extant populations of cheetahs have been affected by these bottlenecks. One study by Dobrin et al. Analyzed single nucleotide variants and mutation accumulations across cheetah genomes, specifically highlighting AKAP4, a gene correlated with reproduction. The researchers discussed modern cheetahs exhibiting traits correlating with the effects of inbreeding and, more troubling, inbreeding depression. Their analyses showcase accumulations of several deleterious missense mutations in these gene regions being correlated with impaired fertility and reproduction mechanisms, such as an increase in malformed sperm cells and inefficiency when forming zygotes. In other words, inbreeding resulting from the previous bottlenecks has limited cheetah populations' abilities to reproduce, which lowers their fitness. Another recent study by Prost et al. Provides a genome-wide comparison across all extant cheetah subspecies. The study confirmed cheetahs having lower heterozygosity compared to other medium to large feline species, while also revealing that the severity of high inbreeding and low heterozygosity varies between every subspecies, especially threatening Asiatic and Northwest African cheetah subsets. These results have not only showcased the effects of inbreeding from such bottlenecks, but also the implications for conservation being imperative across different populations. Although these results are grim, such genomic analyses of cheetahs have provided us with new insights into the species' prehistoric roots and plights that have led to the modern species and genomic details we see today. However, it also illustrates the importance of recognizing and understanding genetic bottlenecks in extant species. The reductions in both population size and genetic variation can influence the trajectory of not only a population's allele frequencies, but an entire species' evolution, limiting the survival and fitness of individuals within these affected extant populations long after these bottlenecks have occurred. I hope this account provides an in-depth understanding of this mechanism and its effects on populations. And with that, This has been a Natural History Vignette. Thank you for watching.